So we continue with the second talk. It's also a pleasure to introduce, for me to introduce you to Professor Tore Hägglund from the Lund University. He has an impressive experience in process control and especially in PID control. He has written 3 different books together with Professor Carl Johan, as you saw before. I like a lot the way in which Tore writes his papers, because he makes everything easy to understand and read. So this is very good for us. And also I like a lot his experience with industry and this kind of courses that he teaches at the industry in Sweden. And Tore has been here in Almeria for 7 times or 8, we don't know exactly. So we can say that he's already Almeriense. So please, Tore.
Thank you very much, José Luis. Yeah, and thank you very much for inviting me here again. I really enjoy these visits to Almeria. I've got so many friends here in Almeria, and we have had so many nice collaborations. And I like the city, and I like the landscape, so yeah, I'm enjoying it. What I will talk about today is research in the regulatory control layer. You will soon understand what I mean by this. I have to adapt to this one. This pyramid is a description of the process control instrumentation that we have. We can divide it into 4 different layers. On the lowest level, we have the field devices. We have the pumps, the sensors, the valves, and so on. And on the next level, the regulatory control layer, we have all our PID controllers, and we have the complicated network that combines all the PID controllers. On the next level, we have the advanced process control, mainly MPC or GPC. And then even higher up, we have production control. So what I will do is that I will talk about this regulatory control layer. This picture shows just a small part of a process instrumentation on this layer. And what we can see is, first of all, it's complicated. This layer is often built up for a very long time, often during decades, and by generations of engineers out in the process industry. If you look more into detail, you can see that there are some PID controllers. The red circles mark PID controllers in this layer. And we have done quite a lot of research when it comes to the PID controllers in this layer. But there is not much done when it comes to the rest in the layer, the basic structures that build up the whole layer. And what I will do now is that I will give you 2 examples where we have done some research and some improvements related to these structures. And then after that, I will draw some conclusions about why we haven't done more and what should be done. This is a list. Carl showed you a list of recent PhD students that has been working on PID control at the department. This is, I think this is a complete list of PhD students at our department that has been working on PID control, supervised by me and Carl. So quite a lot of research has been done in this area, as I said. But when it comes to the basic control structures, I will give you the 2 examples. The first one is feed-forward control, a nice work that we have done together with people in Almeria and Madrid and Lund. And then I will talk about some recent development about ratio control. Let's start with feed-forward control. This is feed-forward control. You have the process. You have the PID, you have the controller, you have the process, and you have a measurable load disturbance that acts on the process. Since it's measurable, you can use feed-forward. You can introduce a feed-forward compensator that takes as input the disturbance and adds a signal to the controller output. And if you read textbooks in control, you can see that if, and you can also see it directly from the screen, this block diagram, that is if, no, that if you choose, I'm trying, yes. If you choose this compensate, no, okay, sorry. Yep. It's very sensitive, and I will adapt. I'm trying to get, okay. If you choose this compensator in this way, the effect of the disturbance will be totally eliminated. You will not see it in the process output. And that is what you read in all textbooks. If you design the feed-forward compensator in this way, you will eliminate the effect of the disturbance. The problem is that you can almost never realize this compensator. For instance, if the delay in P1 is longer than in P3, it's impossible. It means that you can improve the response. You can improve the responses when you have the low disturbances, but you will not eliminate it. What does it mean? It means that you get a response. I don't know if I'm doing something wrong. Or can we can try this one? Yeah. Now, my own device. Look at this. Look at these two. Here we have a simulation example. A low disturbance. We have two compensators, a static one and a lead lag. A compensator that is a pole and a zero. So look at to the left. If we take the dashed line, is just a static compensator, a gain. We get the disturbance. The controls, we have the feed forward, it jumps down, and this is the response we get. If we have a lead lag compensator, we'll get an improved response, the solid one. This is the open loop case. This is the case when the controller is not introduced. The controller is in manual. Now, if I put the controller in manual, in automatic, you will get those responses. And you see they are worse. The reason is that now the controller, the feedback controller, will start to act on the disturbance. So you have both a feed-forward action and a feedback action, and they both try to solve the same problem. And the reason, the effect will be they overshoot. Now, how should we take care of this problem? There are in principle two ways to do it. One way is to tell the feedback controller that you shouldn't act on this disturbance. The feed-forward part will do it. And the other way around is to tell the feed-forward action, okay, you can do something, but you should take into account that the feedback controller will also work on this problem. The first solution was presented we found a paper by Brosilov and Joseph in 2002. They extended the structure, the feed-forward structure, so they told the feedback controller that you should be careful. And if you choose this compensator H in this way, then you are back to the open loop case again. If you have this extended structure, you will get those responses also in the closed loop case. So that is one solution. The other solution is to tell the feed forward controller that you should take the feedback controller into account. And this is a very nice story, because in March 2010, me, Sebastián Dormido, and José Luis, we were sitting in Manolo's office at the university, and we discussed interactive learning modules, and we were discussing an interactive learning module for feed-forward control, and how should it be designed and so on. And then Sebastián said, there should be a design method for feed-forward control. And this was in 2010. And it seems that nobody has said this before, because at that time there were no simple feed-forward design methods available. So José Luis and I, we started to work very extensively. We sent email back and forth. I went home to Lund and we sent email back and forth. And we came up with a design procedure that was published in 2011. And this design method takes the feedback controller into account. And here you see the responses. Here you have the if you take the static compensator, the dashed one is the one that you saw before, and the solid one is our new design feed forward. And over here, you see a lead lag compensator. The dashed line is the one that you get if you don't take the feedback controller into account, and the solid one is the one that we get, where we minimize the integral absolute error. So a very nice collaboration. So that was my first example. Let's now go to the second example, ratio control. Ratio control means that you would like to keep the ratio between two signals, normally flows, at a certain rate. Suppose that you have a factory where you mix blue and yellow components to produce a green one. And what you would like to do is to have the same ratio, the same color all the time down here. You're of course also interested in the flow, but what I'm talking about now is when it's the most important topic is to keep the ratio. This is a very common problem. In furnaces, for instance, you would like to have the ratio, and boilers, you would have to keep the ratio between air and fuel constant. You have blending, inline blending in chemical plants. It's a very common problem. I made an investigation. I asked some different companies in Sweden, how many ratio control problems do you have? And in a normal paper mill, you have around 250 ratio control problems. It means that around 15% of all controllers in a paper mill are working on ratio control. So it's a common problem. Okay, is it a problem? Let's see. So you can see it as a 2x2 problem. You have two valves or pumps. You have two measurement signals, two flows, and you have two set points, the flow and the ratio. So you would like to keep the ratio between the two flows constant. I call this ratio A, and you would like to keep a certain flow. I put in this talk, the flow set point is the desired flow is the desired flow on this in this first loop. You can have the total flow as well if you want. Now, there's no problem to keep the ratio during steady state conditions where you don't have any disturbances. But you will also like to keep the flow when you have set point variations, when you have low changes in the flow, when you have low disturbances, for instance, caused by pressure variations in some of the tubes. When you have saturations, when one of these valves becomes fully open and fully closed, you still would like to keep the ratio. And it's also an advantage if you can keep the flow also when some operators switch one of the controllers in manual mode or to local set points. So you would like to keep the flow also during all these disturbances. Now, how is it done today? There are two methods that you can say form the industrial standard. The first one is what I call the parallel ratio station. You take the external set point, you multiply it by and feed that to the first controller. You take the same set point, multiply it by the desired ratio, and that forms a set point to the second controller. This is a kind of open loop approach. You take the flow set point, multiply it by the desired ratio, and you give the set point to the two loops. Does it work? Yes, it works for set point changes. If you make a set point changes, and if you have tuned the two loops for the same dynamics, same responses, then it works. But it will not work if you get low disturbances, if you have saturation limitations of the control signals, or if some of the controllers are in manual mode. It will not work because this is an open loop approach. About half of the applications that you find in industry are run in this way. The other ones are run in this way. This is a kind of master-slave approach. The set point is still fed to the first controller, but the second one is not following that set point. The second one is following the actual flow in the first loop. So the second loop is a slave loop that follows the actual flow in the first one. How does it work? Well, there's an advantage. You have some problems with the set point because the second loop is delayed now. It's following the actual flow. It means that if I make a set point change, the first loop will follow the set point, but the second one will follow the actual flow. That means that you can't keep the ratio during the transient. But the advantage is that if you, for instance, if this valve becomes saturated, so you can't keep the set point, well, this flow will follow the actual flow. So it means that if you have a limitation in this valve, yes, you can still follow the ratio. You have a master and slave configuration. But still, you see, you have some problems. So, what I suggested is another structure that is slightly more complicated, but I would say just slightly. And the idea is to switch the roles of master and slave between the two controllers, so that the loop with the largest control error becomes the master, and the loop with the smallest control error becomes the slave. It means that the controller that has, well, if some of the controllers run into problem, it will become master, and the other one will try to help him, her, by follow the flow. So this is the basic. This is the idea. In fact, this is the only slide I could have shown on this one, but I have some more. This is a symmetric approach. The master and slave roles are switched all the time. There is no one single master, one single slave. You can implement it in using standard blocks in DCS system. I will show you an example. We have implemented it in an ABB 800 system using their standard blocks, and you need some. You need to take absolute values. You need some relay logic here, but it's not that complicated. How does it work? I will show you some simulations. Here we have. What do we have? We have the two process outputs, the two control signals, and the blue one is a set point. Here I show you a set point, a step change in the set point, and you see that the decide ratio in my simulations is 1. The decide ratio is 1. So I would like these two curves to be on top of each other, the solid and the dashed one. And you see, they are almost on top of each other, but the price is that we have some kind of switching strategy. We switch the role between master and slave. It means that we switch each controller. The set point will be switched between an external set point and the other flow signal. Do you like that signal? No, you don't like that signal. But this is the price that you have to pay. If you are really interested in keeping the ratio between the two flows, this is the price that you have to pay. Okay, we can make a trade-off. If we go back, here is a hysteresis. I don't have to switch immediately when between master and slave. We can put in a hysteresis. If I do that, okay, then it will look like this. I will not keep the ratio as before, but this is for most applications good enough. You can also put in rate limitations and so on in your controllers if you want, but there is a trade-off. There is a trade-off between the accuracy in keeping ratio and control signal activity. Low disturbances. Here I simulate low disturbances. At this time, the solid output, the solid loop gets a low disturbance, and you get the deviation here. And you see, at the same time, it becomes master, which means that the other loop tries to find its friend up here, and here they will meet, and then they will go together down. So there is a transient where we don't keep the ratio, but in this part of the transient, we keep the ratio. Here's an example of a control signal saturation. I limited one of the signals, the dashed one, to 45%, made a set point change, and we are not able to reach the set point, but the focus was to keep the ratio. So this is the flow that we'll get, and we keep the ratio. And this is a situation where I put one of the controllers in manual mode and make step changes in the controller output, still keep the ratio. So it works. I've tried it out in a paper mill in Sweden. We implemented the strategy in, as I said before, in an ABB 800 system, and we tested it on a section where they produce hydrosulfite is used to bleach the pulp, and it is produced by mixing 4 different chemicals. Well, water is a chemical. Water, boron, SO2, and NaOH. We could have handled all the 4 flows. Then we would have had 1 master and 3 slaves at the time, and then we would have mixed it. But we didn't. We just looked at the water and the boron flow. Before they used the parallel ratio station, they had added some logic to reduce the total flow if some of the valves would become fully open for security reasons. But okay, we took water and boron. I will not show you the details, but here we have the water control loop. It was a loop in, there was a valve in bad shape, stick-slip motion. You can see here that you have stick-slip motion over here. The sensor was good, the noise level was low. In the borer loop, we had a pump that was in good shape, but it was a noisy signal and there were low disturbances. So it was a mix. This part had a bad actuator but good sensors, and in this part it was the other way around. What do we see? We see 2 set point changes, but in the first one we limited the controller output so that we were not allowed to reach the new set point. But the important thing is that we managed to keep the ratio. This is the desired ratio between the 2 flows, and this is the actual flow. So it worked in this environment, this bad environment. Here we have another situation. Here we changed the controllers. We put the controllers in manual and made manual changes. And we still managed to keep the ratio, except in this case. And the reason is, you see that the water flow, this loop is very fast. I make a change in the controller output, and the water flow response comes immediately. And the boron flow, the pump in this loop, is slower. So for that reason, we are not able to keep the ratio. But the nice thing is that it worked. It worked in this environment. So, what one should do is, of course, we implemented it in this way, by the standard blocks that were available in the DCS system, ABB 800. What one should do is, of course, to create a new block. We should have a new block in the DCS system where we have as input the 2 flows, the desired ratio and the desired flow. And as outputs from the block are the 2 desired set points that should be fed to the 2 PID controllers. Okay, now I've shown you 2 examples of developments that we have made in this regulatory control layer. But there's not much more to tell about research in this area. I would say this is an area where you find very little research and development. And then the question is, why is it so? I think I have part of the solution. the answer to the question. You know that we have had several technology shifts when it comes to the instrumentation in process control. We had the pneumatics in the early days, 100 years ago or so. Then they turned to analog electric devices. And at the end of the 70s, beginning of the 80s, they moved from analog instrumentation to digital instrumentation. I call this the digitalization area. And these technology shifts, they are often abrupt and unplanned. They are often caused by pressure from competitors or customers. And they often mean that you have to replace people at the R&D. Take this digitalization. You have all these people working in pneumatics and analog electronics. And then suddenly they wanted to move to computer-based equipment. They have to employ new engineers from the universities. And it had to be done quickly. And in this transient, there's a big risk that information is lost. And there's also a risk that you don't take advantage of all the potential of the new technique that you are installing. And what happens, I realized it many years ago, but Carl mentioned the 4 or 5 years I spent in industry. It was in fact exactly during this transient. And it was a very exciting time when the industry shift from analog instrumentation to digital. And what happened was that they were in a rush. They copied what they had and implemented it in digital devices. Here you see an analog controller from the 70s. And here you see a digital one, same company, the company that I worked for. And you see that they are quite similar. They would like, the goal was to keep the panel for the operators. They shouldn't bother about this new technique that was behind. So they look very similar. One thing this was a period when we worked with the auto-tuner and the gain schedule. So it was a good time to, in this chaos, you could say, it was also a good time to, in fact, invent some new ideas. So the auto-tuner was something that was where they took advantage of the possibility of the new technique. But look at the controller. Look at the front. You had about the same type of bar graphs as you had before, because the operator wanted to see it in this way. This was also the time when the DCS systems and the PLC systems started to appear. This is a control room from the 80s, the 70s perhaps the 70s, or 80s. And you see the panels with all these single station controllers with all these bar graphs. This is a picture of the STM20 system that Carl-Johan mentioned before, where you introduced the auto-tuner for the first time. And look at the screen. You see the bar graphs again. The goal was to keep the operator should feel at home, so to say. You should have the same appearance. So what happened during these years, and this transition was, before the digitalization, if we look at this pyramid again, of course we have the field devices. We always have the field devices. What happened was that in this regulatory control layer, the equipment was replaced. The analog equipment was replaced by digital equipment, but they just copied and make digital versions of it. And then they left it. And the only research, almost only research that was performed in this layer was about the PID controller, PID design. These two layers, they were performed by humans before the digitalization. We didn't have any computers here, so it was the operators, engineers that performed these more advanced planning and so on. After the digitalization, the academia went for these two layers. Here we have had all these advances in MPC and GPC control. But this layer was neglected, more or less, I would say. It's okay, but there is another problem, and it is that the different layers here rely on properly working lower levels. If the valve doesn't work, okay, we can try whatever we want in this layer. If the valve doesn't work, we can't do anything. So this layer must be in good shape if these layers should work properly. And this layer, if this layer should work properly, this layer must also be in good shape. David Ender, the founder of Techmation, once said that regulatory control is the foundation for advanced process control. Everyone knows that you can't build anything lasting on a poor foundation. That's especially true when adding advanced process control over basic regulatory control. So I think there is much to gain in focusing, spending more research and development in this layer. These basic control structures that we have, cascade control, feed-forward control, they are used so many times and so many processes. So if you make an improvement, a small improvement, it can have a large impact. And as I said, it's also important if we should succeed in this layer, this one should also be in good shape. I used to say that suppose that you are developing a Formula 1 car, and you are just focusing on aerodynamics and the engine, and forgetting the tires. Then you will run into problems. And the tires, in process control, the tires are the equipment, the PID controllers and the basic control structures that you find in this layer. And process industries have bad tires. There is lots of fun improvements that can be made in this layer. And we can improve, we can find a new strategy, not only improving the current strategies, but also find new strategies. Okay, thank you very much.
Thank you very much, Tore. So, any question? Yes.
In your ratio controller, the switching is still going on. In the ratio controller, the switching is still going on during the steady state all the time, all along the steady state of the.
No. I think I show you some simulation. If you have this hysteresis. If I'm now a master and you're a slave, we will not switch until your error is a certain amount larger than mine, so to say. So there is a hysteresis. So in steady state, no noise, nothing. No switching.
Okay. Tori, can you put the list of the regulatory receipt that you provided at the very beginning? It was...
that one?
Yeah, that one. Yeah. I agree with you that one of the problems is that in most cases all this title is only, in most cases, provided only by industrial people in control. And also, I agree with you that we need people doing research from an academic point of view in order to provide some kind of fundamental principle in order to attack all these different things, taking in the same philosophy in order to provide all this one. You have provided two very nice examples, ratio control and feed-forward control, of course.
Yeah.
But all this, I remember that in the second book that you write with Carl Armstrong, you provided many examples about split rate control, selective control, mid-range control. I think that could be interesting in order to provide some kind of common basis in order to attack all these problems.
I agree.
I think that could be interesting because I agree also that we can provide using this kind of a basic control strategy better control, because if you provided advanced control MPC, but the lower level layer is not doing well the things, it is not a good strategy.
No.
What do you think would be interesting? First of all, in the curriculum for teaching to our students, in many, many cases, we don't split nothing at all about all these elements. This is my feeling perception. Probably my colleagues say, no, I explain all these elements, but I am almost sure that we explain another thing, but we don't explain this thing. Could be interesting to provide this kind of strategy, because if a student don't feel that we have this kind of problem, probably we have not any possibility to do this kind of research. And my second question is that if you examine the publication about basic control strategy, in the last year, well, perhaps filtering, cascade control, but the other things here are not
some
very
papers
well
about feed forward. Work on feed forward.
Yeah.
We had a PhD thesis about feed forward.
I think that your message is very important. The people need to put in action in order to solve this kind of basic problem. That because we have a lot of things to do in order to improve the control layer. Okay. What do you think about that?
I agree. I would say we teach, we talk about cascade control, feed forward control, and filtering in our basic course. Nothing more. I think these 3 dots are also interesting. I would like to see new. I mean, now we have improved current strategies, but I would like to see. There must be new interesting coupling strategies that we haven't thought about.
Yeah, but for instance, the cascade control, and this is very important from my point of view, the only simple rule that we explain to our students is, you in the internal loop, you provide this proportional controller, and then you give all the regulatory capability to the external loop, providing a PI controller. You have 3 parameters, but I think that we can do more in this kind of control loop, because in many, many occasions, cascade control is a very important in process control. You can find in the different PID scheme many cascade control, and probably they are novel tuning, and we can do a better job in order to improve this kind of basic control strategy. Okay.
And I personally, I think we have lots of discussion about this, but personally, I would like to have integral action in the inner loop as well. But there are different opinions about this. And another interesting topic is anti-wind-up for cascade control. So as soon as you start to dig into some of these structures, you will find interesting problems.
Okay.
So.
Yes, very interesting talk. Thank you. Well, I would like to talk about in industry. Most of the processes are several. So if you want to have the tires in good shape, as you say, well, you have to solve that coupling at that level. I understand that feed forward can help, that ratio is a kind of multivariable, but I think that the coupling that is in that list is very important, because, well, if the regulatory level is not well, then you have to rely on the advanced control, maybe on NPC, but you cannot solve that decoupling. My question is, are you working on that, or the research group working on decoupling or?
Decoupling. Yeah, we have done we have had some interesting collaboration with people down in Cordoba. We have a student from Cordoba visiting us, and we did some work about inverted decoupling and so on. So we have done some work, but I think that there are other groups that have done much more.
And do you think that NPC can be considered as in the regulatory layer as a multivariable controller that solves that problem?
My opinion is that you should try to solve as much as possible in the regulatory control layer. And the things that are not solved in the regulatory control layer should be left for the MPC. That's my opinion.
Thank you.
Okay, and what's your opinion about people who says that the advanced control level give us a common framework to substitute a lot of ad hoc strategies for specific units? I mean, the low-level controls and single loops are stay, but you have to implement different strategies like cascade, feed-forwards, selective, or eliminate or erase all these ad hoc strategies and put a MPC, for example. That gives a common framework for control a lot of units or different processes in a multivariable way.
Yeah, it is a common framework. On the other hand, I'm not that experienced in MPC, so I should. But my impression is that it's a very complicated framework. I talk about this ratio controller in a Nordic meeting a month ago, and there were people from former Statoil, now Borealis, and they're really, really good at MPC, and they claim that no, we would like to have ratio controllers at the bottom. We don't want to solve those problems in the MPC. We would like to have them solved in the regulatory control layer. So, but it depends on who you ask.
Any other question? Okay.
In relation with the use of MPC in the regulatory level, I agree with your opinion, because I think that you try to put MPC in the regulatory level, you are hidden the knowledge of your process. You have the right position in order to use the MPC in the advanced in the layer that you are providing. And I suppose that in many cases, if you know your process very well, you are modeling and something like that, you can obtain better improvement using basic strategy that could be translated to the MPC in the higher level. Supporting your opinion with respect to what Carlos said, I suppose Carlos is an expert in MPC control, and probably we need to speak a little bit more about that.
Yeah.
Okay, so thank you very much again, Tore, and we have also a person for you. Okay, so now we have the coffee break out of the room. We will be out around 30 minutes. Afterwards, we will start with the Pechacucha session. So please, all the students who has to present come to me before leaving the room to be sure that everything is in the computer. And remember that we have to sign your certificates. So yes, you can leave the certificates in the desk, in the registration desk, and Ramon will be there to sign. Okay, thank you.